Welcome. So in this lecture we're going to explain what logic gates are and how the processor works internally. This is important for you to understand so you understand how our assembly language is working. Now essentially what happens is an instruction is binary, right? And it gets passed through a circuit in the processor which results in an outcome. And how these are integrated in the processor is by using what's known as logic gates. Logic gates are basically the way you position transistors to make certain logic happen, such as an AND gate or an OR gate or an XOR gate. Each of those gates do different things. So we're now going to explain what all of those gates do, and I'm going to hopefully give you more of an insight of how instruction sets work. Hey guys, okay, so I've got a little circuit simulator here and I'm gonna try to explain how the instruction sets in a processor work. So I'm gonna get rid of this for now. Essentially, in your processor you have what's known as an instruction set. Now all an instruction set is circuits arranged in a certain way. And obviously they're quite complicated because they're the fundamentals of your processor core. So you have you have circuits such as the ALU, which is responsible for adding and multiplication, stuff like that, mathematics. And our actual instructions are also passed through this. And essentially when we write assembly and we pass it through an assembler, is converted to its binary equivalent. So I'm just going to make a simple circuit here now just to try and explain some of this stuff. So I'm going to add a new AND gate, and I'm going to go like this, right? So what the AND gate does, it takes two inputs. If both are 1, outputs are 1. So let me add in a power source to that. So you can see I've added a power source there, and I've added a power source here. So if we run that now, so if you run that now, you can see that because both of these are on, the output is on. If I turn one of those off, the output is off, right? On, off, on, off, on. And I turn this one off, that one goes off. Turn this one on, but turn this one off, then it goes off. So the AND gate basically says if both inputs are 1, then the output is 1. So why am I explaining this? Well, think of these things here as the data pins on your processor, right? Essentially, when it reads your instruction in, these data pins will be filled with these currents, these voltages, the current from the voltage, right? So it's either high or low. So in this case, we have, in this little example I've made for you here, we have data pins that it has 2 data pins, right? So what would happen is when it loads a byte from memory, it would fill these data pins with the value of that byte, and obviously there would be 8 of those or whatever. It would assign the lower 8 pins, right? And then it would pass it through a much more complicated circuit than this, and it would figure out which instruction that you are trying to do. So for example, these two here can be expressed as 1, 1, which equals binary 3, decimal 3. So because binary 1, 1 equals decimal 3, essentially in this little circuit I made here, this tiny circuit, one of our instructions is binary 1, 1 or decimal 3. And if you pass in that instruction, binary 1, 1, we just get an output here. Now in your processor it's going to be more complicated than that. So decimal 3, this is just an example now, might mean move register AL to register AH. Now obviously we haven't really gone too in depth with registers yet, but all you need to know is registers are basically tiny storage inside the processor itself, outside of RAM. So in that case then, decimal 3 or binary 1 as can be represented here, the current will go in here, the output will be 1, and then it will start, and then it will go through all the circuitry to actually move the value from the capacitors and move that value to the other capacitors, to move the value from one register to the other, for example. But that's a lot more complicated. But I hope this kind of makes sense, because this is how the process works internally, but it is done on a much more complicated level, and there will be a lot more circuitry involved to perform some of the operations. This is just a simple AND gate to show you that on the lowest level, these are the building blocks, and you would have thousands, millions of these in your processor to make it work. Okay, so let me now show you an instruction set, and we can go more from there. So if we look by here, this is the instruction set for the 8086 processor. This is the we've been using MU8086. This is simulating this processor essentially. So you can see it has quite a few instructions here, and in the processor will be loads of circuitry like the ones I just did in that circuit simulator, but a lot more of them and more complicated. There'll be a lot of those so that when it receives the data, the binary equivalents of these instructions, it knows where to route the electricity, the current in the processor, which makes certain things happen, right? So for example, if we look at the jump instruction by here, let me just take you to that. You can clearly see here, it says an unconditional jump transfers control to another part of the program. So what this does, this here would basically, once assembled, the binary equivalent of the jump instruction would change the program counter register. And by the way, the program counter register holds the value of the instruction in memory, in RAM, that you're currently executing. So it holds the address of where that instruction is. So for example, in the Hello World tutorial, I told you MS-DOS loads us at 100H, right? Well, in that case, when it jumps to us, the program counter will be 100 hex. That'll be the value of it, right? So when we call the jump here, what we're basically doing, we're just changing the program counter register so that it points to another part in RAM. So then, in the circuitry level of your processor, the binary equivalent of this jump instruction, it would go through all the AND gates and all that, and all the gates until it gets to the circuitry in the processor responsible for copying the value you want to jump to the program counter register. So that's how it works. It's all just clever circuitry, and it's all built on logic gates. Okay, so I'm going to just quickly write a little program just to show you what I'm talking about. Right, when I do JMP $, that means to just keep jumping to the same position. It's basically infinite. It'll constantly jump back to line 7, right? So it'll never end. I just want to show you that because it's a nice simple instruction. If I press emulate here, now you can see here to the right is our assembly, and to the left is what's in memory at that address. So you can see that the opcode for jump, JMP, is 235 decimal. So if we now convert that to binary, you can see that 235 decimal is this binary value here. So back at my circuit, essentially you see that we have two of those lines here, right? We'll call them data lines. You would have 8 of those, right? And then these values here will be passed in. So if it's 0, then it will be off. And if it's 1, then it will be on. right? And then that goes through all of the logic gates to produce an output like this one here. And then obviously whichever part in the process it outputs to, it would deal with that operation. So in our case, we're doing a jump, right? And now if we take a look at the second byte here, we see 254, which is the value, because here we say jump 100H, right? Because when we do jump $ here, it takes our current address, and when it assembles, it replaces that with the address that we're currently at, right? Which is 100H. So that's how it's an infinite loop, because it'll keep jumping to itself forever, right? But so these two bytes make up that jump instruction. You have the first byte here, decimal 235, binary equivalent by there. And what that is a jump instruction. And then the jump instruction expects a second byte, which is where you want to jump to. And in our case, it's 254 decimal, right? So that is how it works, essentially. So if we now run this, you can see it's an infinite loop. So that's what that jump does there. But I hope that makes sense about how the processor works, because by explaining the circuitry like this, hopefully it makes a little more sense. So when we assemble our assembly code, it becomes machine code, which corresponds to the instruction set here. And by scrolling up, we can see all the available instructions. And there's different variants of these instructions as well, by the way. But your assembler will choose the right one. So you don't have to worry about that. So basically, your entire processor has an instruction set. And this is the readable manual. And how the instruction set is built into the processor is that it's just logic gates and transistors that make up different connections and rules of how the data can be transferred along the circuit, and it uses it just uses physics to do that, basically. Like with the transistors, you can change the way the current flows. So that is how it works. So now that you understand that, hopefully now that clears that part of the course up. But you can drop me a message if you get into trouble with that, because it is a complicated subject. I hope you've enjoyed these course previews. To purchase the course, please use the link in the video description. Every course purchase allows me to make more content and keep bringing value to you.